Assalamualaikum and greeting everyone. For this lecture week 11, it consists of two parts. For this video, I will cover the field procedure part, which is quite straightforward, while the next part is a little bit more technical that require me to explain to you during the class hour. So this is basically the seismic event or seismic signal that being recorded where we have the linear signals of refractions or the head wave and also the direct wave, the red color on top of it, while the reflection signals shown in hyperbola or curved line as shown in the figure, where for this case we have three reflectors with its features of bending signal or bending curve. As discussed during the previous class, the zero offset acquisition is considered the ideals where the source and the geophones are at the same locations. While achieving this ideal setup is almost impractical, meaning that it's almost impossible to be done, it is required due to its significance in addressing travel time and NMO issues that will lead to velocity calculations later on. In seismic reflections, the prevalence acquisition method is the common midpoint CMP techniques that we will discuss later, and sometimes is also known as common dead point or CDP. However, CMP is widely utilized ataupun being used as the common term, while the term CDP is specifically applicable only when dealing with a flat reflector. So just now we talk about the CMP methods. So why not we just go through with the CMP method? So basically the CMP method is known to be multifold reflection. So we need to understand the term folds later on. And this involves deploying multiple sets of sources and also receivers denoted in red and green respectively in this figure. And the diverse information captured in the trace form is subsequently combined or stacked to enhance signals to noise ratio, resulting in a single or singular trace or single fold stacked outcomes. So the fold of the stack is determined by the number of traces in the CMP gather. So to understand, let's take a look on this picture. So this picture shows the common midpoint gather or CMP gather. So the red color over here or the red dot over here is representing the source, while the green dot over here is representing the receivers, while the yellow over here is actually the midpoint. So the common midpoint gathers here shows that all the receivers actually recording the same reflection point. Okay, regardless the offset, all the receivers recording the common midpoint or common reflection point or common dead points. Because of this, all the seismic receiver will produce traces, individual traces. For this case, since we have 5 receivers, so we're going to have 5 traces of the same reflection point. So what we need to do next is we're going to sum it ataupun combine it. So in seismic term, we call it as we stack it from these 5 traces. We stack, combine to make ataupun to produce a single or singular trace or a single fold stacked outcome. Okay, so when we're doing this, we actually increase the signal to noise ratio. So that is the purpose of this CMP method gathering. So the basic understanding on how the CMP method is actually been produced is illustrated in this figure on the right. So in order to get a common reflection point at this particular points, the acquisition setup is always need to be set up as end-shot techniques, where we're going to discuss this later. End-shot techniques. So where this is when the shots always in front of G1 or geophone number 1. After a shot is applied for the first time, the acquisition setup will shift to the right. So we're going to shift to the right, bring all the instrument together, bring it to the right. With the same spacing, same interval between the offset and also interval between the receiver. And the acquisitions keep continuing until, for this case, we have 6 shiftings, meaning that 6 survey for this case, and also 6 shots is produced. So in order to get a good signals or resolutions at the same reflection point over here, so we are going to sort it so that each acquisition, we have 6 acquisition here, will pointing at the same reflection area or reflection point. So acquisition 1, in order to get this reflection point, it is quite straightforward lah, where it is between S1 and also geophone number 1, quite straightforward. However, in order to get the same informations at the same location or reflection point, for the acquisition 2, we need to consider S2, in that shot number 2, and also geophone number 2, since we are shifting the distance between S2 and geophone number 2 is increasing in order to get the same reflection point. So we need to consider S2, G2. And as for acquisition number 3, 4, 5, so it will keep increasing in terms of number of geophone and also number of shot. Again, we look at the acquisition number 3. We have a shot number 3 and also geophone number 3 that pointing at the same reflection point. And it goes with acquisition number 4 for S4 and G4, S5, G5, and S6, G6. So by doing this, we are actually recording the same reflection point 6 times at 6 different source locations. So by doing the CMP method, the raw data that related to the CMP method, where we have 5 geophones, but for this case we're going to use the 6 signal of the 6 geophone. Okay, we'll have the curve shape like this due to the distance increment. Okay, for example, over here S1 and G1 is quite short in terms of the offset, while for the S2, G2 is getting greater and greater. So that's why we have a kind of delay in terms of signals. So after we got the 6 individual traces, that later we're going to combine or stack, that been explained earlier, so that we want to make a single trace, since it only require one trace to represent the vertical informations of the subsurface. We don't need the 5 or the 6 traces, because at one single reflection point we only need to have one trace to represent, oh, here, over here we have the reflection point, we have the reflector. So we're going to produce a single trace from out of this 6 trace. So how we are going to do that? So we are actually doing what we so-called as the normal move out or NMO corrections by using these equations. So the purpose of doing the NMO corrections or normal move out correction is to adjust the delay time arrival due to the offset of the signals, so that they will align together horizontally. Okay, meaning that we are going to bring all the delayed data from the different offset into a single aligned flat signal. So this is basically what I mentioned to you just now, where we are going to align, brings all the delay of the signals of 6 different offset geophone from 6 acquisitions. We try to bring everything so that they will align in a single horizontal data like this. So in order to produce this kind of data, we need to do the NMO corrections by applying a correct NMO velocity. So once they are aligned to each other, but for this case it's a flat, so it's quite straightforward. So we easily can align all the traces into a horizontal data. So after you do that, we're going to combine everything from this all 6 traces into a single stack. Again, we only need to have one stack traces, one stack trace for a single reflection point to represent a reflector is actually been recorded at that particular point. So again, after the signal align to each other, we actually can continue to conduct the stacking process where we combine all these 6 traces to become one. So by doing this, we are actually increasing the signals to noise ratio, because if we understand the concept of superpositions, when we have a maximum amplitude and then we have another maximum amplitude, we combine, we will actually increase the amplitude. However, when we apply the NMO corrections or NMO velocity, we need to be aware with the terms over corrections and under corrections, or over corrected or under corrected. So these are the two common terms to express in terms of failure in applying the correct NMO velocity in the NMO corrections, meaning that the process to align all the traces into a single horizontal strata too. So when the NMO correction is done improperly, so it will result the overcorrections, while if the NMO correction is insufficient, so undercorrections will occur. Okay, so let's take a look on the overcorrection first. So again, when the NMO correction is done improperly, it will result overcorrections. Okay, overcorrections like here. So it will shift the seismic occurrence in the time domain excessively. So this usually occur when an excessive height assumes NMO velocity is utilized for the adjustment. So instead of they go with a flat strata, they overcorrected. So overcorrected meaning that it moving above the straight line, moving above the straight line when we apply the NMO velocity ataupun adjustment. So the ultimate subsurface image may be inaccurate as a result of the reflection from deeper subsurface layer being pulled too close to the horizontal axis. So this geological structure can be distorted by overcorrections, giving the impressions that they are shallower than they're supposed to be. Okay, supposed to be they are going to this way, but instead they're going upward. So that's why you're going to have this kind of signals. So where we're supposed to have our reflection point over here, but because of this we might misinterpret that we have over here. So this is because um, the amplitude is not properly combined or stacked because of over corrections. Okay, so that is going to be a problem when we overcorrect it. And then we also have the under corrections or under corrected. So this is when we apply the NMO velocity above what we're supposed to apply. Okay, for example, the correct NMO velocity is 1700 meter per second, but we apply for 2000 meter per second. So it's going to have a kind of issue, what we so call it as under correction. So under correction, which means that the seismic event are not sufficiently corrected for fluctuation in subsurface velocity. So when the assumed velocity is too low, So this kind of frequently happen. Because of this, it's possible that the reflection from deeper level will appear to be deeper than they actually are in the time domain. So under corrections may cause deeper structure or deeper features to look more extended or dispersed than they are actually, leading to an incorrect interpretation as well. Okay, for example, so they're supposed to be a bit shallow, but because of undercorrected, the NMO alignment, see it goes downward, so you got it appear to have a multiple signals of amplitudes, so you might misinterpret it. Probably you pick at the bottom part, or probably you pick at this part. So because of this, we might lead to incorrect interpretations of the subsurface structure. So this is basically how the CMP, or basically the seismic reflection acquisitions, being conducted. But in order to explain more in detail, I show you different picture. We already discussed this before, couple of slides before, and but in order to explain in terms of fault, okay, another terms that you need to be familiarized in the seismic reflections, I will re-explain again lah. So again, we're going to have this kind of techniques. We call it as the end shot acquisitions, where the positions of the offset ataupun shot is always at the front, meaning that the shot is always before the first geophones. Okay, we have shot number one, geophone number 1, 2, 3, 4, 6, and so on. So for this case, we have again the source is red and the 6 yellow triangle are all the receiver, and all the receiver will receive a signals from a respective reflection point. Okay, for example, shot number 1 and geophone number 1, we have the reflection point over here. Reflection point number 2 is between shot number 1 and shot number the geophone number 2. So once we finish shooting, okay, we then move into the next location. Okay, for this case, we are moving to the left. So and then we acquire again, and then the acquisition process is repeated as before, as usual, as like what we did for the acquisition number 1, which is shot 1, and then the receiver will record the signal from some reflection point. For example, over here we can see some reflection point, and and the process keep continue until it covers all the study area. For this case, we only have 3 acquisitions lah, and then if you want to continue, you can continue further. Now we're going to talk about the CMP fault. Okay, fault. So the things that I said earlier, which is very important. So fault is starting to build up. Okay, macam mana dia build up, how it build up after a few shots. For this case, 3 shots that being acquired, where the fault in this contact is the number of overlapping reflection point ataupun redundancy of reflection point from these 3 seismic acquisitions. So we have 3 seismic acquisition. Some reflection point will have redundancy. Okay, 3 CMP faults. Okay, we have 1, 2, 3. The number over here is representing the CMP fault. The 3 CMP faults over here at the middles, meaning that it's actually the same reflection point that was hit by all the 3 acquisitions. So all 3 acquisitions hit at this 2 reflection point. Okay, as you can see here, you see the ray pass. So meaning that we have 3 CMP fault. Meanwhile, 1 CMP fault over here, meaning that 1 reflection point out of 3 different location of shots. So meaning that we have 3 acquisitions. Out of 3 acquisition, and at this particular reflection point, we only have 1 fault. Only 1 reflection ray pass has been passing through from these 3 acquisitions. Okay, again, let's say we have a CMP fault, 2 CMP fault, meaning that out of these 3 acquisitions, only 2 acquisitions that reach at this reflection point. Only 2 out of 3 acquisition. So in general, the reflection point spacing is always half of its receiver spacing, because the distance on the surface is always half. So that is another general knowledge that I want to share to you. Let's say we have 5 meters apart between the stations ataupun between the geophone. Geophone 1, 2, 3, 4, the interval is 5 meter. So we need to expect that the interval of the reflection point will be half of the half of the interval ataupun geophone interval. Let's say this is 5 meters. So the interval between the geophone, the reflectors reflection point is 2.5. And in general, let's say we have a total layout of, let's say, 5 meters. We have 6, roughly we're going to have 25 meters layout on the surface. We need to expect that we're going to have half of 25, which is 12.5 meters of coverage area, okay, at the reflector. So that is the things that I said earlier. The reflection point spacing is always half of its receiver spacings on the surface, because the distance on the surface is always half between the source and geophone, or geophone to geophone. So one more example, when there is only one shot, the receiver will only receive the signal from every single reflection point. Hence, the build-up number of fold is 1 only. So then we have another shot. So the entire equipment arrangement then shift to the left. So the number of fold start to increase. Okay, based on how many ray paths that hit the same reflection point after we shift our acquisitions. So in general, the middle sections always has the most fault, as shown earlier, or as shown in the previous slide. As we go to the middle, the number of faults will keep increasing. But however, this slide is actually try to aim the relationship between the geophone spacing, which is always half of the underground reflection spacing. Okay, for example, this spacing, let's say 5 meters with 6 geophone, 25 meters. Bawah dia ataupun at the bottom, at the reflection points, the total length from this first reflection point until the last reflection point is the same. Not the same, half of the total length on the surface. Okay. Okay, so after data acquisition has been conducted, the resulted data can be actually rearranged, or we call it as resorting. We sort again for the purpose of either pre-processing stage or during processing stage or post-processing stage, because at certain level of processing we need to rearrange it into a certain gather, a certain arrangement, or certain sortations. And when we go into another stage, we need to rearrange into another sortations. So there are 4 types of common data sortations, namely common short gather, common midpoint gather, common receiver gather, and lastly we have common offset gather. Regardless the terms, all these type of data sortations all will give you the hyperbolics downward, okay, meaning that the increment of the offset, except for the common offset gather. Okay, you are going to have a flat data. Okay, I will explain that later. So let's go with the common short gather first. So common short gather is the first raw data that we obtain after we conduct the acquisitions without sorting, meaning that without sorting, the raw data, the first raw data we obtain is actually in a common short gather. So it means literally that the receiver, the green dot over here, receive the signals from a common short, from a single short. So this is what it means by common short gather. So vice versa, we have common receiver gather. So this is the other way around. So this one, when we have a single shot, we have multiple receiver. This one, from multiple shot for common receiver gather, we only have a single receiver, meaning that this single receiver will receive the signal from a series number of source. Okay, we just need to sort it. If you remember the acquisition, we have multiple acquisitions. We just need to sort it out. And then we also have common midpoint gather. This one I don't need to explain lah, because we already discussed this earlier about how it looks like. But basically, it's a common sortation process where most of the processing stage require a common midpoint gather, especially for enhancement of the signals. This gather from a multiple number of sorting, of course, and we sort all the data that hits at the same reflection point, okay, as we discussed earlier, or sometimes we call it as the midpoint on the surface. So this method involves recording seismic signal at a different offset from common midpoint. So common receiver done, and then kita go straight to the common offset gather lah. So common offset gather is a bit different. Again, the signals that we obtain is always in the curve shape, the curve shape, regardless the type of gather, common short gather, midpoint gather, or receiver gather. However, common offset gather is different because we try to maintain the offset, okay, between the source. So let's say we pick the offset between 5 meters, meaning that S1 with geophone number 1, S2 with geophone number 2, S3 with if 5 meter, meaning that S1 with geophone number 1, S2 with geophone number 1, S3 with geophone number 1. However, when we want to increase the offset, let's say we want to have an offset of 10 meters, S1 will geophone number 2, S2 will geophone number 2, S3 will geophone number 3. So we try to maintain the offset. So because of that, the data that you will obtain or rearrange will produce a flat horizontal line compared to the rest. Okay. So as we discussed earlier, CMP gather somehow can be equivalent to the CDP if the reflector is flat, but it will not be always the case lah. Okay, it will not be the case if the subsurface is irregular or the reflector is dipping. Okay, and the reflection will be scattered, and we call it as a displacement of the max and minimum distance of reflection as smear. Okay, as the ray path is always obey the Fermat principle, so that's why CMP is no longer equivalent to CDP. So the next corrections we need to do is deep move out instead of normal move out. We need to do deep move out for the CDP correction, so that everything will peak at the same reflection point. Okay, after we do the deep move out, we will get the same reflection point regardless the situations underneath. Okay, I think that's all for the first part. We will continue the second part in the next class hour.